Hello friends, this is Professor Cotter. In this video we are going to look at solving one more example of rational inequality. For this one I'm already giving it in the factored form. So we have f of x equals x plus 3 squared times x minus 2 times x minus 4 all over x plus 3 times x plus 1 squared times x minus 4. And so for this one, we want to solve f of x is greater than or equal to 0, and then also f of x is less than, f of x is less than or equal to 0, and then also f of x is greater than 0. So I'm going to start by finding my zeros, my wholes, and my vertical asymptotes. And so in this case, wholes, zeros, and VAs. So in this case, we've got a couple of interesting things going on. First, we undoubtedly have a whole at x equals 4. But then we have something interesting going on at x equals negative 3, because we notice that there's a factor. There's actually two factors of x plus 3 on the top and only one factor of x plus 3 on the bottom. So if we canceled, we'd still have an x plus 3 on the top. And so it feels like this may be a whole. It's on both the top and the bottom. But it also may be a 0, because when we cancel, we're still left with an x plus 3 on top. It actually turns out, in this case, that this is a whole. And that's because if I try to plug in x equals negative 3 into this function, I'm getting both a 0 on the top and a 0 on the bottom. And so it's not an x-intercept, it's a whole. What is going to happen is that this whole is going to turn out to sit on the x-axis. So if you filled in that hole, the function would have a 0 there. Its y value is 0. But the function is still undefined there, and so it has a whole rather than a 0. For the zeros, the remaining factor on top is x minus 2. So that's equal to 0 when x is equal to positive 2. And the remaining factor in the denominator is x plus 1 squared. That's equal to 0 when x is equal to negative 1. And so these turn out to be all of the behaviors where the graph can switch from being positive to being negative. What I'm going to do now is I'm going to create my sine graph. And I'm going to put all of these behaviors on the number line. So we've got negative 3, we've got negative 1, we've got 2, and we've got 4. And let's see, negative 3, that's a whole. Negative 1, that's a vertical asymptote. I like to sketch these in just to remind myself what's going on there. At 2, that's a 0. And at 4, that's a whole. From here, I'm going to break it up into zones. So this is zone 1 to the left of negative 3. Zone 2 is in between negative 3 and negative 1. Zone 3 is between negative 1 and positive 2. Zone 4 is between 2 and 4, and Zone 5 is to the right of 4. And I'm going to pick a test point in each zone. So I'm going to choose negative 4. I'm going to choose negative 2. I'm going to choose 0, 3, and 5. And what I'm going to do is I'm going to plug each of these into my function and determine whether the function is positive or negative there. You can do this by hand if you really want to, what I'm going to do is I'm going to cheat a little bit, and I'm going to use my graphing calculator just for the sake of time. So I'm going to go ahead, and in my graphing calculator, I'm going to graph this function. So I'm going to do x plus 3 squared times x minus 2 times x minus 4. And I'm going to divide that by x plus 3 times x plus 1 squared times x minus 4. And I'm going to use my table in order to identify the y values for these. So I'm going to go to my table, and I'm going to delete out whatever I have in there. And now I'm going to put in -4, -2, 0, 3, and 5. And when I do, I get corresponding y values to those. I'm actually going to take a snapshot of this and bring it into my notebook. So when x is equal to -4, y is positive. So we are positive in zone 1. In zone 2, we get a -4, and so we're negative. In zone 3, we get a negative, and so we're negative. In zone 4, we get a positive, so we're above the x-axis. And in zone 5, we're still positive, so we're above the x-axis. So now, last but not least, what I want to do is interpret this sign graph as the solution to my inequalities. So for part A, we want to solve f of x is less than or equal to 0. This means that I want the solutions are going to be those parts that fall below the x-axis, so the negative zones. So that's going to be zone 2 and zone 3. So for zone 2 runs from -3 to -1. -1 is a vertical asymptote, so it gets a parenthesis, in union with -1 to 2. Now 2 is a 0, and my inequality contains the condition of equality, so that's going to get a bracket. If I want to write this in set notation, we're going -3 is less than x is less than -1, or -1 is less than x is less than or equal to 2. In part B, we want to solve f of x is greater than 0. So those are the zones that fall above the x-axis, the positive zones. So that's zone 1, zone 4, and zone 5. Since it's a strict inequality, I can use all parentheses. It doesn't matter whether it's a 0 or a whole. So we're going to go -infinity up to -3 in union with 2 to 4 in union with 4 to positive infinity. Last but not least, if I want to express this in set notation, -3 to -2 is x is less than -3, or 2 is less than x is less than 4, sorry, advanced the slide on accident, or 4 to positive infinity, that's x is greater than 4. And so that turns out to be the solution to part B. And that's how we solve a rational inequality.